Good afternoon, everyone. So today I want to continue with some applications of Ampere's law, some major examples of applying Ampere's law. So we did Ampere's law for a wire, thin wire, and then we imagined that it has some thickness to it. Actually, it's easier to imagine a wire's thickness than a wire that has zero width. Okay, and then we formulated the magnetostatic field for both those conditions, both those configurations using Ampere's law. We assumed an infinite wire, infinite transmission line, and this is an example of something with a high degree of symmetry. The other example that has also a high degree of symmetry is an infinite sheet. So if I have, let's say, an infinite sheet, right? Some sheet, right? And this sheet has, let me draw it as an infinite sheet, right? It's an infinite sheet like this, and it extends in all directions. So it's infinite in all directions, right? And then there's some current flowing to it, right? So I can observe this infinite sheet from the side. From the side, of course, it will look like this. It will look like a line, right? This is the edge of the sheet. So this is edge of sheet. And then it extends to infinity, right? So the idea now is that current is flowing through the sheet, right? And it's distributed along the sheet. So if we take a certain, first we have to determine, is the current flowing from our perspective, from this perspective, is the current flowing into the board or out of the board? So let's choose a current that's flowing out of the board. So I represent that by dots. Right? The infinite amount of current filaments are flowing outside the board and towards us. Right? And this is an infinite sheet, so there's an infinite amount of current, of course, but what we can talk about is we can talk about line current density, meaning how much current flows per unit length. So this is, let's say this is a 1 meter length, 1 unit length, right? Then JL is going to be the amount of current flowing in 1 meter. So that's line current density. It's the amount of current flowing in 1 unit length of 1 unit width of the sheet. So what about the current flowing in a general width? So let's say this is W, right? The amount of current flowing in the width W of the sheet is going to be GL times W. Now this is a problem where we can apply Ampere's law, right? So because this is a problem with a high degree of symmetry. So let's go back to the Biot-Savart law. So let's say I want to find a field at some point here, right? So each filament, right? I have to sum up over the infinite amount of filaments, right? But each filament will have this as R, let's say R hat, and then the element is going to be moving with the current, right? And then moving outside the board with the current, right? And then using the right hand rule, the field should point this way, H. What about if I take an element from filament from the right, like some distance to the right? So if I take this new R hat, right, and the filament again is the current is flowing outside the board, so using the right hand rule again, I get that H from here should be this kind of field, H1, let's call it H1. And then I move the same, I take the filament to the left side, and I again apply the right hand rule, I get this field, H2. Right? So from the symmetry of the problem, at each point I can take the contribution from some filament from the right and from filament from the left. I end up with a situation where the vertical components cancel each out, right? And then the horizontal components reinforce themselves. So I end up with a situation, let me draw it again here. I end up with a situation where from symmetry, I can deduce that the field is going to always be in this direction when I'm above the sheet. And again, from I drew the dots. Okay, the currents are flowing in the sheet. And then from underneath the sheet, again using the Biot-Savart law, right? Current is flowing out, the directional element is flowing out, the position vector is going down. Using the right-hand rule, the field should be pointing in this direction. So from symmetry, we know what the direction of the H field is above and below the sheet, and we know it should be the same everywhere, right? Because it's an infinite sheet, it's symmetrical. If you have an infinite sheet and you increase your height by a certain amount above the sheet, it doesn't matter. It will still look like an infinite sheet. So that's what's nice about studying infinite sheets, right? Although they don't exist, right? They're a good approximation to a situation where you have some surface where current is flowing, and you zoom in into a small portion of the surface. When you zoom in, it looks at that small portion, and you get close to the sheet at that small portion, it looks like an infinite sheet. So it's a very good approximation. And we did those kind of approximations in electrostatics when we studied the field due to infinite copper plate, or infinite conducting plate, or infinite charge plate, infinite transmission line. So the same kind of thing we did for electrostatics, we're repeating for magnetostatics. Okay, now the question is, what is the Amperian surface, not the Amperian surface, the Amperian contour that I can use to calculate Ampere's law, to find the field due to this infinite sheet? Well, I can pick this contour. Right? I can, with the width W, right? And length, let's call it L. L wouldn't matter because as I'm integrating along this contour, so I'm moving in this direction, let's say, as I'm integrating along this contour, notice I picked my direction to be counterclockwise so that I'm always in the same direction as the field. But notice as I'm moving over those parts, those segments of the contour, the field is always 90 degrees with my displacement. So the dot product inside the integral will always be 0, right? I will only get a contribution to the contour integral, to the line integral, in this portion, on the horizontal portions of the path. So if let me do my path integral now. So if I go and say, hey, closed surface over C, this is C, path of H dot dl equals I enclosed, right? This is Ampere's law. What is I enclosed? I enclosed is JL W. That's from the definition of the line current density. And then I can take H out. And then I'm integrating over W twice. I'm integrating over W here and then over W here. So I'm going to get 2W. Right? So I end up with this expression. W cancels with W, and I end up with this expression for the magnetic field intensity. The magnetic field intensity is going to be JL over 2 amps per meter. Okay, and this is the result that we got pretty easily, I would say, for an infinite sheet. Okay. Next example I want to go through, also an interesting example and a very common thing that you would encounter, is the toroidal coil. And this is a very common design for an inductance. We haven't talked about inductance yet, but we will. but you would see designs where you have something like a toroid material, right, with a certain permeability, right? We said permeability is mu, right? But then there's a wire. Let me do it in another color. There's a wire that's kind of twisting around the toroid. This is called a toroid, right? So something like, I'm drawing it terribly, I'm sure, but right, and it comes out. Right? So the thing, so the current is twisting in and then coming out in this manner. Now the question is, what is the field due to this torus? And let me show the cross section of this thing. The cross section of this thing is like this. So we have, right, and then we have the it's like, looks like a donut, right? And then the current is spun around those upper and lower portions of the toroid, right? And then this is the center axis of the toroid. This distance here is A, and then this distance to the edge of the toroid is B. Right? So the question is, what would the proper Amperian curve be in this case? Right. First, what do you think would the field uh, look like? Like, I mean, let's look at the Amperian contour first. I would guess an Amperian contour would be something like this. I could pick this Amperian contour. So this is like this surface. So the inside of this contour is the surface that's at the center, right? So this is the center of the contour, right? This is the center of the surface of the contour, right? So to look like this, notice here we have currents coming out of the surface inside enclosed by the contour and coming into the surface enclosed by the contour. So we're constantly having current coming out and coming in, coming out and coming in, coming out and coming in, right? So naturally that means that the total current flowing into the surface enclosed by the Amperian contour is going to be zero, because any current coming out is always going to be coming in. So naturally we would expect any field outside the toroid to be zero. H outside the toroid to be is expected to zero. Similarly, if my contour is inside the toroid, I would expect also H to be zero, right? So the toroid is configured in a way such that all the magnetic field is concentrated inside the toroid itself. Only when I use an Amperian curve C that is smack in the middle of the toroid like this is the Amperian curve, sorry, let's call this C, do I get current flowing in the surface enclosed by the contour. Of course, how much current is flowing into that surface is going to be not just I, it's going to be dependent on the number of turns of the toroid, right? So the current is going to repeat, is going to go into the surface enclosed by the contour n times, depending on how many times we turn the wire around the toroid. So this is the total current going inside the surface. So n, the number of turns of the toroid, plays a big factor in the magnitude of H. So let's apply Ampere's law. So integrating over the contour C of H dl. And again, very simple to apply. This equals I enclosed. I enclosed is Ni, right? And then H is constant. You can take it out from the symmetry of the problem. And then I'm integrating on a circle. So let's call this distance of the contour is R. The contour could be at any distance, right? The contour could be at any distance from the center. We want to solve it in general. Okay, so H 2 pi R equals Ni. So H equals Ni over 2 pi R. Okay, so this tells me that the field intensity, the magnetic field intensity inside the toroid is dependent on how close we are to the center, which kind of makes sense. The further you are from the center, the more spread out the field is. But it's useful sometimes to calculate the average field. So let's say I said this is A, the small axis is A and the big axis is B. So H closest to the center at the edge before we go into the middle free space portion of the toroid is going to be Ni over 2 pi A, and then H2 at the outer edge is going to be Ni over 2 pi B. Typically what people do is they're interested in the average field. They assume that that's sometimes easier to calculate and assume that there's an average field inside the toroid instead of dealing with a spatially varying field. You assume there's some average constant field. So constant field, that's the average of the field inside. And one way of averaging is taking the smallest amount of the field plus the other extreme and dividing it by 2. That's the average, right? So H average would be Ni over 4 pi. 2 turned into 4 because I divided it by 2. 1 over A plus 1 over B. So this is also a useful expression that you would see. And what about the flux density, magnetic flux density? It's just a matter of adding mu. If the inside of the toroid is air, just air, we say mu naught. How can you hold the wire? Well, let's say you have the wires and you hold them rigidly in place, and there's nothing inside but air. When we discuss magnetic materials, you'll find out that we could also put some material in there. Similar to when designing capacitors, you might want to put dielectrics in there to increase the energy that you can store inside the capacitor. In a similar manner, what you could do is you can insert a special kind of magnetic material in there to increase the value of B, to increase mu. But let's assume it's air. If you assume it's air, you get mu naught over 2 pi R, and then B average, of course, is going to be mu naught Ni over 4 pi 1 over A plus 1 over B, where B is the field that's going to depend on the material. Okay, and H has units of Ampere per meter, and remember B has units of Weber per meter squared or Tesla. Tesla is the SI unit, or the more official unit. I don't remember if it's the SI unit per se, but it's popular. But I prefer Webers per meter squared because it has more physical sense to me. It's analogous to Coulomb per meter squared for D, right? And D essentially has units of electric charge over distance squared. In the same manner, B, when I think about it, I think about it as having units of magnetic charge over distance squared. Weber is a measure of the magnetic charge if it existed, right? It doesn't exist, but nothing stops us from imagining that if it existed, it will have those units. All right. So this is the toroid, and then the third example I want to go through, and this is something that also you will see a lot if you're dealing with magnetics, is the field due to a solenoid, field inside a solenoid. What is a solenoid? A solenoid, well, long solenoid or infinite solenoid, right? Because we want to do some approximation here, right? Solenoid is something where I just have twisty wire like this in a long, right? This is what you would think an inductor would look like. Typical archetypical inductor would look like, just twisted wire like that, right? And then if the length is short, you get something more of a coil, right? It's just nomenclature, just language. But having a solenoid like this is interesting because it now gives you a good way to approximate the field within it, right? How would you use this picture of a long solenoid to approximate the field within it? You can imagine that you have a surface and you take a cross section of the solenoid. Although this is a cylinder, if I rotate this surface, there'll be symmetry. The intersection between the solenoid and that surface will always look the same. What it will look like? It will look like a bunch of wires very close to each other with current. I'll use dots to represent current moving outside the board, so on and so on, and it's long, so that's why we assume it's gonna go infinite, right? And then a bunch of wires going into the sheet with currents that are moving into the board, which I represent by X's. Okay, so this picture, what does this picture looks like? This picture looks like exactly similar to the infinite sheet situation, right? Only now we have two infinite sheets. So regardless of the angle of the surface that crosses the solenoid, we always get a situation, a picture that looks like two infinite sheets, right? So from the symmetry, we can tell that we can combine the field coming from the two infinite sheets to get the total field. So remember when we discussed a sheet, infinite sheet with the current going out of the sheet towards us, we said that the fields look like this. Top above the sheet, the field is going to go in this direction. I think we did this. Yeah. So above the sheet, the current is going to go, the field, H field is going to go in this direction. Below the sheet, the field is going to go in this direction. What about the situation where the current is flowing into the sheet? Again, from using direction from the Boyer-Savart law, we deduce that the field under this kind of sheet is going to go have H that goes in this direction, and above it is going to have H that goes in this direction. So this is case 1 and this is case 2. What happens when we combine two sheets like that in parallel? We can apply superposition, right? Always. I mean, superposition, if there is one true fact about electromagnetics, like what's one thing that you should ensure you tell someone so that they can rederive electromagnetics from scratch? Well, one of the facts, there are a bunch of facts, maybe 2 or 3, not a lot, surprisingly. But one of the major facts is superposition. Superposition always applies. Right? So using superposition, if I am outside, if I'm here, some point here, this sheet is going to give me a field that goes in this direction, and this sheet is going to give me a field that goes, so here I am both underneath both sheets, right? So this sheet is going to give me a field that goes in this direction, and the other sheet is going to give me a field that goes in this direction. The fields cancel each other. If I'm in this region, this lower sheet is going to give me a field that I'm above now, right? So give me a field that goes in this direction, and this upper sheet is going to give me a field that's going to go in this direction. The fields are going to cancel outside the solenoid. If I now test a point in the middle, inside the solenoid, the lower sheet is going to give me a field in this direction, and then the upper sheet is going to give me a field in, let's see, oh sorry, I did it wrong. The lower sheet is going to, I'm looking here, the lower sheet is going to give me a field in, I'm above it, right? It's going to give me a field in this direction, and the upper sheet is going to give me a field in the same direction. The fields are going to reinforce each other, and I end up with the magnetic field only existing in the middle of the solenoid. The question is, what is the magnitude of the field? And to find the magnitude of the field, we need to apply Ampere's law. Okay, let's apply Ampere's law. The first step to applying Ampere's law is finding the Amperian contour, where we integrate h along, right, equals I enclosed. Okay, yeah, something else I forgot to give you about the solenoid. So there is a certain, when you're winding a solenoid, when you're, you have this thing and you're winding it, there's a term called the winding density, meaning in a unit length, how much windings do you have, which is n. So n is the number of windings per 1 meter, per unit length. In our case, the unit of measurement for length is the meter, so it is the unit length. Right? So depending on how much compressed the windings are, how much dense they are, you'll get a different n. So if you could fit, and of course that depends on the thickness of the wire. If you have very thin wire, you can fit a lot of windings within a certain unit of length. Right? And the field turns out to depend on that density of windings, okay, because it determines the current. So let's do that. Let's find the Amperian surface that we are interested in. So we discovered that there is a field inside the solenoid that's in this direction, right? So let me pick the Amperian surface to be something like this, contour to be something like this, surface, sorry. And then the field here we said is 0, right? And the field here inside the solenoid is pointing to that direction, and the field here is 0. We've established that for the solenoid. So if I pick this contour and I pick the directionality of the contour to be counterclockwise, the field along those perpendicular lines will be, the field here will be multiplied by the displacement, right, dotted with the displacement, but they are 90 degrees with respect to each other, so that will be 0, right? So this whole portion of the contour gives me 0. The only portion that gives me anything is this portion, right? And let the width of this contour be W, right? And then yeah, so this integral becomes h times W. What is I enclosed? I enclosed is just the density of the windings, right? How many windings are there per unit length? So this is number of windings per length. Well, what is the length? What is the total number of windings inside this Amperian contour? It's the number of windings per length times the length. The length is W. So this is the total number of windings, and each winding is carrying a current I, right? It's the same current I that's wound across the inner cylinder. So it's going to be NW times I. That's the total enclosed current. W goes with W, and we end up with this very simple equation for the magnetic field intensity inside the solenoid. We end up with H equals N I ampere per meter. And if I wanted to find the flux density, I just multiply mu naught N I. Right? Mu naught for air is by definition, we selected it to be that way. Because remember, I said I think what matters in electromagnetics is the product of mu naught and epsilon naught. You can select in the SI system of units, if we select mu naught to be a certain value, that will determine epsilon naught. Right? You have a degree of freedom of selecting one of the units, and for historical reasons, people selected mu naught to be 4 pi times 10 to the power minus 7. So you have that degree of freedom, you fix it for mu naught, and you get the appropriate epsilon naught for air. The real physical constant in electromagnetics is the speed of light, c. C is 1 over square root, turns out to be 1 over square root mu naught epsilon naught. This is something perhaps that you will study when you take the part 2 of this course. Okay, but this is the magnetostatic field for the solenoid. Okay, right, and those are the 3 major examples about applying Ampere's law that I wanted to go through. And as you've seen, I mean, for many problems, it's a very simple law to apply. Okay, I want to talk a bit about the magnetic flux density. What is the meaning of the magnetic flux density? Well, from the mathematical equation, the flux density is just equal the permeability times the magnetic field intensity. And contrast this with the electrostatic case, where the flux density equals the permittivity times the electric field intensity, right? And we said here that the units of epsilon, I'm just reviewing here, are the units of D, which is Coulomb per meter squared, right? The flux density turns out to be Coulomb per meter squared, and then which is the same units as the polarization vector, because D turned out to be the field. D is a polarization vector, essentially. It's the way of representing the electrostatic field through its polarization effect of space, right? And then E has magnitude of what does volt per meter. We use the volt designation, right? So this is Coulomb per meter squared divided by volt per meter, it becomes times meter per volt. So we end up with Coulomb over volt times 1 over meter, right? So we said this is kind of like a capacity parameter. This is like how much charge we get, polarization we get in space due to a certain voltage that occurs in space. So if epsilon is larger, that means per meter we get more charge, polarization charge. I mean, space remains neutral, of course, but we get more polarization charge per unit of space per voltage difference. So this is somehow measuring the capacity of space, and we end up with a unit that measures capacity of electrostatic energy, which is the farad. So this unit turns out to be farad per meter. So in the same manner, we want to study the units of the permeability. So those are the And in the same way where the units of D were Coulomb per meter squared, the units of B are Weber over meter squared, right? And H is what? So we know that H, we defined it as ampere per meter. Notice the nice duality here. Coulomb, we said, is the unit of charge for the electrical charge, and Weber is the unit of charge for the mathematical magnetic charge, which doesn't exist, only currents exist, and divided by volt over meter. E has volt over meter, H has ampere over meter. So you notice this nice duality. It's like they're mirror images of each other. So we continue with this, and we end up with Weber over meter squared times meter over ampere. I end up with Weber over ampere times 1 over meter. This again is an interesting unit. This also seems to indicate some kind of capacity. So this is the per amp, how much magnetic charge can we get in free space. So this is kind of like a measure of the capacity of space or of the material or whatever. And this unit, when it comes to capacity of magnetic charge, the mathematical magnetic charge versus current, is called the Henry, right? So mu has units of Henry per meter, where Henry is just Weber per amp, just like Farad, Farad is Coulomb per volt. Always be mindful of this mirror, the two words, the electrostatic word and the magnetic word, and mirror images of each other than this curious lack of symmetry, in the sense that electrical charges exist, but magnetic charges don't exist, right? Electrical charges and their currents exist, but magnetic charges and their currents, although mathematically describable, they don't exist, but they're still useful to think of when you're thinking of the units. Of course, the other common unit instead of Weber per meter square is Tesla. So Tesla is the flux density, right? And just like if we take D and we integrate it over a surface, we get something called the flux instead of the flux density. So you get the current density, you integrate it, you get the current, total current. You get the flux density, you integrate it, you get the total flux, right? So we can get electric flux, which is not very common thing that you see, but for magnetic fields, it's very common to talk about the total magnetic flux. So it's very common to see people talk about the magnetic flux flowing through a surface, right? And that's just the integration over the surface of the flux density. So you integrate flux density, you get flux. This is now a more common entity. You see this used especially in transformer design or in machine design. People use this a lot. There's nothing special about it. It's just the same. I mean, as we could talk about magnetic flux, right? But we could also talk about electrical flux. It's just the act of integrating a flux density vector. Okay, so this is what the term magnetic flux means. Now, one thing, and perhaps we will talk about this in more detail when we talk about the properties of magnetic materials. So we talked about in the electrostatic case, we modeled space itself as having bound charges in it, bound dipoles. And when an electric field occurs, field intensity occurs, those bound dipoles stretch, right? So we end up with something like this, right? And this is called polarization, right? And it is the effect of this polarization is included in D, is built in, embedded in D, because the way we achieve this is by when we calculate the polarization, we try to figure out what kind of volume charge density occurs according to polarization, and we take that volume charge density due to the bound polarization of the embedded dipoles in space or in the material. Those are charges that are not free, that cannot move. So we take that and we embed it into the axiom of first axiom of electrostatics, Gauss's law, and we use that so that to make D a vector that represents both the polarization of free space, embedded polarization of free space, and on top of it, the polarization of the material, right? So that's how you interpret D. In the same manner, you can interpret B as a polarization of dipoles in space, but those dipoles are not electrical dipoles now. We now need to imagine that in all of space, at each point of space, there are bound charges that cannot move, but can stretch and orient with respect to the magnetic field intensity, but those are magnetic dipoles, meaning we imagine that there are hypothetical positive and negative magnetic charges, QM positive and QM negative, that could stretch and orient as if they are, right, dipoles. So I'm putting plus minus, perhaps I should put north south, right? So those are magnetic dipoles. What you need to imagine is you need to imagine two magnetic charges, one positive, one negative, with a certain distance between them, and depending on the H field, those dipoles stretch and orient, and we can use the same theoretical exposition to arrive at B being really a polarization vector of magnetic charges. Right? So it is the same thing. It's analog. It's exactly analog to the electric case. Right? The only thing is that in the magnetic case, it's not called polarization. It's called magnetization. The thing that happens to the embedded dipoles in space is called magnetization. It's called something different, but it is the same phenomena as polarization. It's the same thing as polarization. It's just called different for called differently for historical reasons, right? And then there's, of course, the tricky thing is that magnetic charges don't really exist. So this is really just a fiction of our imagination. Well, the math is correct. The key thing is that mathematically it is correct and it fits within the theory. And if you are uncomfortable with imagining magnetic charges, people also imagine, for magnetic dipoles, they imagine little loops of current. So they imagine little loops of current that can orient themselves and can expand in magnitude, meaning the current in the little loop di could go higher or smaller, larger or smaller, right? And the little loops in the material can, or embed in space, can orient themselves. So this is another way of imagining magnetic dipoles, which might seem more physical, right? Because we know that electrical currents exist, right? So we could imagine magnetic dipoles as either those loops of current or those dipoles D and of magnetic charges, plus QM minus QM plus QM minus QM. It doesn't matter. The mathematics is the same. The same we can say about electrical dipoles. Electrical dipoles, we studied them first as, you know, those collections of positive, negative electrical charges with a distance between them. They can stretch and orient. So those are electrical dipoles. Right? We get the same mathematical equations if instead of those dipoles looking that way, we imagine them to be loops of current. But now they are not loops of electrical charges moving. The current is not constructed from electrical charges. The current is a magnetic current, meaning it's a current it's a bunch of charges. It's a movement of the hypothetical magnetic charges. So this current is consistent of magnetic charges that are moving in a loop. It's a magnetic current. It's not an electrical current, right? This doesn't exist in nature, and in the case of the electric field, right? But the dipoles, it could exist and exist. And in the case of the magnetic dipoles, this picture does not exist in nature, but the loops of electrical current do exist, right? So that's why people are more comfortable representing electrical dipoles as those charges with displacement between them, and magnetic dipoles as loops of current, right? That's fine. It doesn't matter. What matters is that all four formulations of dipoles give you the same mathematics, right? And you can think about them interchangeably. Okay, we'll talk about this more when we talk about materials, but just keep in mind it is the same treatment that we did for the electrical case, right? With magnetics, it's kind of like there are more nonlinear effects. Materials could saturate, while in electric static case, materials break down rather than saturate. So you might have some magnetic material that gets magnetized. When I say magnetized, imagine polarized, but in the magnetic case, right? So they might get magnetized, but then they saturate this, they reach a limit, and the magnetization stops. That tends to happen in magnetics. In electrostatics, what tends to happen is that there is no saturation. What happens is that the material keeps polarizing until it breaks. There's a breakdown that happens. Okay, so I think I went on a tangent too much. So the final thing I want to discuss in this lecture, which will going to bring us full circle, is everything we discussed in electrostatics led us to finally build two postulates for electrostatics. So we built Gauss's law. So we started Coulomb's law. We studied the potential function, right? And then we packaged all our results into the two postulates, which is divergence D equals rho V and curl E equals 0, where D equals epsilon E, right? So this is postulate 1, this is postulate 2, right? Postulate 1 is called Gauss's law. Postulate 2, I don't know if it has a name. I don't think it has a name. Okay. Now the postulates of magnetostatic, in a similar manner, we can write from all the results we got, we can write postulates of magnetostatics, and we want to specify them again as a divergence and a curl. Remember, the Helmholtz theorem is that states that to specify any field completely, you need to specify its divergence and curl. So if we want to use postulates or define postulates that specify the field completely, we better be defining a divergence and a curl, right? So the first postulate of magnetostatic, it has to be some divergence, right? What did we learn about magnetostatics? We learned about the magnetostatics that divergence of B is what? We learned that in nature there is no magnetic charge, there is no rho m, there is no magnetic charge, magnetic north, where all the field lines come out like that. They always come in pairs. The magnetic fields always come in loops like this. They loop back to each other, right? So that means that the divergence, if I have any surface here, any field lines entering the surface will always leave the surface. So that tells me that the divergence of B has to be 0. B is a solenoidal field. This is the first postulate, easy enough. And the second postulate is the analog to Gauss's law, which is Ampere's law, which has to do with the curl. The curl of H is what? Is J, the electric current density, right? Where now B, the magnetic flux density, is mu, could be mu naught if it's air, right? Mu naught for air and epsilon naught for air here, or no, not air, vacuum, sorry. H. Right? Those are the postulates of magnetostatics. I won't include the constitutive relationship. Okay, and notice the nice symmetry. They match almost match the electrostatic postulates, except now in electrostatics there is no magnetic current, there is no movement of magnetic charges because they don't exist. So I don't have curl E equals Jm. That doesn't exist. If it exists, by the way, I would have here Jm instead of 0, right? And in the opposite, in the postulates for magnetostatics, there is no divergence for B. There is no magnetic charges, but there is an electrical current, steady electrical current that causes magnetic fields. Right? Of course, I can write those two postulates in their. This is the differential form. I can write them in the integral form, which is the integral over a closed surface is 0, and the circulation of H over a closed contour equals the I enclosed. If I'm integrating over a closed contour C, the integration of H along the contour is just going to be the total current flowing inside the surface, through the surface, embedded in the contour. Right? And this is the integral form of the postulates of magnetostatics. Right? I think this symmetry is quite beautiful, and we're very actually close to Maxwell's equations. Maxwell's equations are just those 4 equations collected together with some other terms added in that hopefully will be very clear given what we discussed about polarization. It will be very clear where those extra terms come, why do those extra terms come in, but we're very close to writing down Maxwell's equations. They're just those 4 equations with some extra terms added in, and you get them. All right, so we'll continue the discussion next time. Right? I think I want to do like a long recitation class after this, perhaps tomorrow, to prepare you for the exam. But yeah, talk to you next time. Thank you guys. Bye.